In today's session, we will try to complete these two chapters. So this is quite a big task, but we will try to do it because of the time limitations, and I think we can do it in a very efficient manner. So let us see what is lumped heat analysis. Lumped heat analysis is basically a type of heat analysis method in which there is no temperature gradient in in the body. So what we saw in the previous chapter, it was pretty simple. There was a wall or cylinder or sphere. Within this body, there was a temperature gradient. Here the temperature was T1 and here it was T2. So when T1 was greater than T2, so because of this temperature gradient, the heat was the heat transfer was possible. But today, in this case, we will look into the bodies where the temperature, now I will draw just the same slab. Here is also T1 and here also the temperature is T1. But the heat transfer here will occur in the form of convection. The heat will be transferred to the atmosphere. So whenever such condition arises in which there is no temperature gradient, within the body, then we can apply the lump heat capacity for the body is negligible. We know that here there is some resistance, that's why the temperature is not instantly same. But to achieve this type of condition where the temperature throughout the body remains constant, we must say that their conductive resistance is almost equal to zero or negligible. Negligible will be the better word, because there is always some resistance present. There is no material in our studies that has zero thermal resistance. So all the heat transfer that will take place will occur on behalf of the conduction. So the external convective resistance will be present there. So we can summarize that the value of H will be small and the value of thermal conductivity K will be very much larger. So in this case, we can apply the lump heat analysis. Now, how can we achieve this in practicality? For practical purposes, we need small bodies. So let's say this is a small, very small me if I'm audible or not. Please write it in the comment. Am I audible now?
Hello, Shubham. Still there is a problem with your voice. You are not audible to us. No, you are not audible. Please check your mic and speaker.
Hello,
Hello.
am I audible right now?
Yes, yes, but voice is very low still.
Okay, actually there is some problem with the microphone. I cannot rectify it right now.
Okay,
Will it be okay if we continue like this?
okay, okay.
Okay, right. Okay, is the screen visible to you?
Yes, now your
Hello?
screen is visible.
Okay, and am I audible? Okay. So yes, so today, sorry for the interruptions for there. We will now restart this session. So we were looking at this lumped hit analysis. So why we needed lumped hit analysis in the first place? So the lumped hit analysis was required because there are certain bodies in which there is no temperature gradient. T1 here is also equal to this T2, which value both values are same. That is that dt by dx, the temperature gradients is zero. So how is it possible according to the Fourier's law of heat conduction? The heat carried away through this body must be equal to minus Ka dt by dx. If this is zero, so this entire heat transfer should be zero. So what we can do here is simply say that there is no heat conduction. The only heat that is transferred through this, uh, the only heat that is transferred throughout this uh, body will be because of convection. So, similarly, the second statement concludes just like that the internal resistance of the body, that is, within this body, there is almost negligible thermal resistance, and outside of this body, there is convection happening for which the convective resistance is predominant. So, Q conduction and Q convection both are playing here the part. However, the R conduction is negligible as compared to R. So now let us just consider a small body. As I told you, we need a small body made up of a material with very high thermal conductivity. In such case, we can apply our lumped heat analysis. So how is it possible? We need a small body just like this. It is at a temperature T1. The temperature here is T1. It is exposed to an ambient where the our atmosphere where the temperature is T infinity, such that T1 is greater than T infinity. Now we know that as the time moves, the temperature of the body will keep on changing as the heat is conducted out. So we can say that the temperature of this body is the function of time t. It is time dependent. Temperature of body is time dependent. So yes, now what we can say here is that this body had some internal energy. That internal energy, let's say, is du equals to mc dt. Now, what is this internal energy? We know that in thermodynamics, internal energy is defined as an energy with it is an energy with which is on account of a body's temperature. So, an energy which is possessed on account of the temperature of the body is known as the internal energy of the of change of internal energy is du by dt, which is mc dt by dt. Okay, now all the heat that was conducted or convected, Q convection, is equals to loss of internal energy. So the all the heat that was lost in convection is equals to loss of internal energy. So we can write that HA for any temperature T minus T infinity, it is equals to minus mc dt by dt. Now the mass we can write it as HA T minus T infinity equals to minus rho Vc dt by dt. What? Okay. So yes, Q convection was equals to minus mc dt by dt. Q convection was equals to minus mc dt by dt. So now consider the same condition. The body is initially at temperature T1 and the surrounding is at a temperature T infinity. What happens when it is exposed to this temperature? The body keeps losing heat. So at any instant, let T be the time. And you can see that if this is time T, so your temperature is the function of this time. So let's now say that theta is equals to t minus t infinity. And we can write it again as, we can differentiate is d theta by dt equals to dt by dt. So the Q convection can we had written at h a t minus t infinity, which becomes Q convection equals to h a theta. And from the previous equation here, here we can put this value h a theta equals to minus. Now mass we can write it as density into volume into C into. Now dt by dt can be written as d theta by dt. We will rearrange these terms and, and we have h a rho v c dt. And we will integrate this from, let's say, point 1 to point 2. So we will have ln of theta 2 by theta 1 equals to minus negative sign h a rho vc into t. While this is the constant value, and this gives us the temperature difference between these 2 points. So if we know t1, we know t infinity, we can find t2 if we have the time t and other constant values which will be given in the problem. So this is a very important derivation here. So if someone is not getting it, one should watch it again and again to understand it. Now, okay, now we derive this equation right now. So we have to now see some terminologies which are originated from the same, which are originated from the same equation. What are these quantities? We have to look it one by one. Now we have time constant tau here. The heading says time constant tau. There is this constant quantity, as I told you, minus HAS rho VC. Let us say I call them, let tau is equals to rho Vc upon HAS. So the entire thing is, AS is surface area. The A that we took was the surface area. Please keep it in mind because it is now convection. It is the now the ball has gone into the park of the convection heat transfer. So as we are talking about convection, we will talk about surface area only. And when we talk about conduction, we talk about cross section area. So the time constant here tau is rho Vc upon HAS. If we put the values of unit here, we will find that the unit of tau comes in second. So essentially, tau is nothing but your some time or some amount of time. Now, what this time amount signifies, what is its significant? So the time constant tau, here you can read it, that the time constant is the same, is the time taken by a body in reaching the ambient temperature when the body is suddenly exposed to. So the body that was which at temperature T1, when it is exposed to temperature T infinity, the time that this body will take to reach the temperature T infinity is the time constant. So when I put this value in this equation, what I get here is this equation. So using this equation, log of theta 1 by theta 2 equals to minus HAS upon rho Vc into T, and putting the value of time constant tau, we can obtain new equation purely in the sense of time constant, which is ln of theta 1 by theta 2 equals to minus T by tau. So what is the next uh, terminology that is originated from this uh, equation? So the next terminology is of characteristic length. The characteristic length LC. We choose our marker here. Okay. So now let's say we have here this entire constant thing tau equals to rho v c upon h into a, area surface. If I take this v by a as, we see that the unit that this quantity will give us is meter cube upon meter square is meter. So this is some linear dimension, either it is radius or length or width or anything. So to include all such linear dimension, we have a broader term known as characteristic length LC, which is equals to volume upon surface area. So this is basically characteristic length. What is characteristic length? Characteristic length is the ratio of volume to the surface area of the same body. Now we have some common bodies such as cylindrical, so this is our cylinder. It has a radius r and length L. So its volume will be uh, its cross section area pi r square multiplied by its length, and its surface area is 2 pi r L. So the characteristic length is pi r square L upon 2 pi r L equals to, what remains here is r by 2. So for cylinder, the characteristic length is r by 2. Now the other important shape or body we have is sphere. So let us assume that this is a sphere. It has a radius r. Okay. So its volume, we know that it is 4 by 3 pi r cube, and its surface area is 4 pi r square. So the characteristic length LC comes out to be, when we divide these terms, 4 pi and r square gets cancelled. The r LC for the cylinder remains r by 3. When I put this value of V by S is equals to LC, we are left with this equation: ln of theta 1 by theta 2 minus ht rho LC by C. Now this is going to be uh, very important formula for us to solve in the exam, because we are not going to be able to find out volume and area each and every time in the GATE exam, as we have almost 2.5 to 3 minutes to solve a question. If we are going to utilize that time in solving the volume and area, so then our lot of time will get wasted. So what we will do instead, we will try and we will try and find out the LC for cylinder and sphere. Just remember this value. For cylinder, it is r by 2, and for sphere, it is r by 3. This is going to be very crucial for saving your time, and such type of tricks are extremely important for solving problems in a very less time. So now the next thing here, we have the Biot number, and Fourier number. These are dimensionless numbers. You have already seen in fluid, I think you may have seen it in fluid mechanics, like Reynolds number, Grashoff's number, etc. Similarly, we have Biot number and Fourier number in case of lumped heat analysis. So what is Biot number? Let us just see what is Biot number. Biot number is said to be the ratio of internal conductive resistance to the external convective resistance. So Bi is equals to, now the Bi is R conduction upon R convection. Fine. What we can do here is, we know that for conduction it is Lc by Ka. The resistance is L by Ka. We can write it Lc by K. This I will not repeat. This was seen in the previous chapter of conduction. And what is R convection? Yes, it is 1 upon Ha. A gets cancelled out. What we have been spared with is H Lc by K. So this is the formula for Biot number, HLC by K. Now there is an interesting fact in regards to Biot number and lumped heat analysis. If Biot number is less than 0.1, only then lumped heat analysis is possible. Otherwise, we will not going to look into this. Why? Because the very first condition we need for lumped heat analysis is that the conductive resistance should be negligible as compared to the convective resistance. So if this condition is satisfied, we can go and carry forward our lumped heat analysis. Otherwise, we cannot go with it. The other dimensionless number is Fourier number. The Fourier number is the ratio of heat conduction rate to the heat storage rate. Now I will directly write its formula here because of the lack of time. So what is the formula for Fourier number? It is given as alpha T upon LC square. Remember, I may have not taken the derivation of general equation in Cartesian coordinate, but I have discussed this term known as alpha. What is alpha? Alpha is thermal diffusivity. What is its significance? It tells you how fast heat can be spread throughout a body. So here we have heat conduction rate represented by alpha and heat storage rate, that is our characteristic length that will be alluded to it. Now alpha we also know that it is equals to K upon rho C Lc square. So this is our Fourier numbers equation. Now see what we can do with these two numbers with our equation. Okay. Now we have this equation HAS upon rho VC. This we can write as H, sorry, it was also multiplied by T. Multiplied by T. Now this can be written as HT upon rho LC into C, because that is the value of characteristic length V by AS. So we know that we can also rearrange this thing as HLC by K. Now see what I did here, I multiplied it with LC and divided it with by K. So to balance this term out, I have to multiply with K and divide by LC, and the remaining term is T upon rho LC C. Okay. So what we have here is HLC by K multiplied by KT upon rho LC square into C. Fine. Now K by rho C is alpha, that we know very well. HLC by K multiplied by alpha T upon LC square. What is this? This is nothing but Biot number. And what is this? This is nothing but Fourier number. putting this value of HAST upon rho LC into C equals to Biot number multiplied by Fourier number. In this equation, we find out that this value entire can be written as Biot number into Fourier number, and the equation that we have here is something like this. So this is also very important formula. So the same equation has different forms. So in the problem, they may give you Biot number, they may give you Fourier number, and they may ask any of the temperature. So with Biot number and Fourier number, without calculating all these things, you can directly find out any missing temperature or any missing dimensionless number. So this is also an important formula with regards to the concern of our saving the time. So these are several forms of the same equation. What are these? The basic equation is this. This is our basic equation. Ln theta 1 by theta 2 HAS rho Vc by rho Vc into T. The second one is of time constant, in which this term can be written as minus T by tau. The third one is of characteristic length, or let's say LC. And the third one is here. So in this way, we have find out the three forms of the same equation which can help us carrying out the lumped heat analysis. Okay, now let's just quickly move to the second chapter of fins that we were going to look today. Now, what are fins? So fins are basically, we know that the convective heat transfer, the convective heat transfer depends mainly upon surface area. Why? Let us just look at its formula. What is it? What does it say? H AS T minus T infinity. What is this AS? AS is surface area. So if we can increase this surface area by any means, then we will be able to increase our convective heat transfer. So in machineries where the heat dissipation is the essential thing, the engineers developed a way to increase the surface area of that machine by providing some extended surfaces known as fins. Now here you can see an engine of a motorcycle. So these are the extended surfaces. What these extended surfaces do, they just increase the surface area of the engine, which ultimately increases the convection heat transfer. So the engine does not get heated up. Similarly, here you can see the condenser of a refrigerator. So here we can see in the condenser of a refrigerator with fins. So what happens here is, as the fins, uh, as the hot refrigerant flows through this pipe, the fin helps them to lose their heat by means of convection. The other thing we have here is of electric motor. An electric motor, you can see in the figure, it is also provided with fins to dissipate heat. Even your laptop, and specifically the gaming laptops, are provided with the fins in order to be able to dissipate the heat as much as possible. Okay, right now the other thing we have is heat transfer rate through fins. Now we have to find out what is the how can we calculate the heat transfer through the fin. First of all, we should be able to know how the heat transfer mechanism takes place in the fins. So let's see that this is a wall. In this wall, the temperature is temperature T naught. It is attached to a fin, and the fin is exposed to an atmosphere of temperature T infinity. T naught is root temperature. T infinity is our ambient temperature. So what happens here is, as the fin is made up of good conductor material, the heat will flow through this. The heat flows through the fin, and here the heat transfer mode is of conduction. So heat is transferred through conduction, and simultaneously this extended surface, because of the temperature gradient, causes the heat to get lost by means of convection. So this is not the similar way that we dealt with the in the first chapter. This is something different. We have not seen something that simultaneously conduction and convection are going through in the same thing. So we need to find out the equations for this. So what we will do is quickly just look into the important expressions that will help us to solve problems. We know that H is the heat transfer coefficient. Let us assume P is the perimeter of fin. AC is cross-sectional area. K is its thermal conductivity. L is the length of fin. And theta naught is what? The temperature difference between root temperature and ambient temperature. So there are two types of fins that we are going to see. Number one is a short fin, and number two is a long fin. To determine if a fin is long or short, we have this condition: ml is less than 3, then the fin is said to be short, and m into l is greater than equal to 3, then the fin is said to be long. Now what is this m? M is a constant which is a replacement of this term hp upon KAC. So m, I will write it here if it is not visible to you. M equals to under root of hp upon KAC. So for short fin and long fin, we have written this thing. So what is the equation for short fin? So equation of heat transfer for short fin is Q equals to under root of hp KAC tan hyperbolic ml into theta naught. I told you what is theta naught. Theta naught is the temperature difference between the root temperature and the ambient temperature. And for this is QS because it is for short fin. And for long fill, it is simply under root of HP KAC into theta naught. So these are important formulas that we have to note down. So the heat transfer rate through the fins can be calculated by using this equation. This is very important thing. M is equals to under root HP upon KAC, where P is the perimeter, AC is the cross-sectional area, K is the conductive heat transfer coefficient, L is the length of the fin. This is L. Now we have found out what is the rate of heat transfer through fin. Now suppose if practically and in exam we need to find out the temperature at this point, which is at a distance x from the root, and that temperature is T1. So how are we going to find it? So that is our next topic about finding out the temperature. So the next topic is temperature distribution of fins. As I told you, the root temperature is T2, T naught, ambient temperature is T infinity, and we want to find out the temperature at the distance x. Let us say T1 is the temperature of fin at distance x. So let us now just draw a graph so that we can simplify the visualization for the temperature distribution. This is our ambient temperature T infinity, which is less as compared to the temperature of the wall. Here the temperature is T naught. As the length increases, the temperature of the fin keeps on decreases. Here the temperature is T1 at some distance x. Here x is equals to 0 at root, and here x is equals to L where it ends. At some distance x, I have to find the temperature T. So the temperature distribution, we need to find out the temperature distribution. The temperature distribution for long fin as well as short fin, both are the different things. But the general equation to find out this equation is theta equals to C1 e to the power mx plus C2 e to the power minus mx. What is this? This is, I think, if you may remember, is the standard solution for the differential equation. So when we solve partial differentiation equations, so this is root for such equations. C1 e to the power mx plus C2 e to the power minus mx. We know what is m. And what is x? X is the distance of any particular point on the fin from the root of the fin. So what is the formula for short fin? Short fin, uh, it is theta upon theta naught equals to cos hyperbolic m L minus x upon cos hyperbolic m. Then we have long fin. For long fin also, the temperature distribution is, it is now here it is different. It is given as e to the power minus mx. So you put the value of x here and value of m. You find this ratio theta upon theta naught. By the way, what is theta? Theta is what? The temperature T at a distance x minus T infinity. So if we know m and x, we can find the value of T because T infinity is given, T naught is known, and e to the power minus mx. So putting this value, we can find the value of T. So in this way, temperature at any distance or any point x from the root can be find out. So this is why temperature distribution of fins is necessary. Now efficiency of a fin. We know that efficiency is always denoted by this letter efficiency of Greek letter eta. So this is the standard procedure for denoting efficiency, and it is given by the heat transferred through the fin divided by maximum heat that this fin can transfer. So what possibly can be the maximum heat that the fin can transfer? Let us see. The root temperature is T naught. The ambient temperature is T infinity. If the entire fin reaches to the temperature T naught, that is the highest temperature available in this system. So the temperature gradient for the heat transfer maximum. So the maximum heat transfer will be HA T naught minus T infinity. I hope you got this concept. What is the maximum value of this. So ultimately we can write is that it is equal to HA into theta naught. So for long fin, we can write efficiency of long fin. This is under root of HP KAC theta naught upon HA theta naught. Forgot to write it down. Sorry for the interruptions. Theta naught gets cancelled, and here we have under root of KAC upon, sorry, under root KP upon HAC. So this is that the value for the long fin. Now, what is now the value of Q fin for, sorry, value of for short fin? Under root of HP KAC tan hyperbolic ml theta naught upon HA theta naught. These things will get cancelled out, and we will have the value tan hyperbolic ml, and the remaining term is the same, which we can write as ml. So this is the value for the short fin. You can easily find out this value if you know this general formula. So this formula here is the important one. If we can just, this formula is important here. Now the next term is effectiveness of fin. What is fin effectiveness? Fin effectiveness is given as the ratio of heat transfer through the fin and heat transfer without the fin. Now we know that this value changes from type of fin. From short fin and long fin, these two values are different. But what about this thing, the heat transfer without the fin? So let us say that we have the same wall here, but this time we do not have the fin. But here we have the cross section area. This cross section area will take part into conductive heat transfer, right? So Q without fin is HAC theta naught, because its temperature is T naught and ambient temperature will be T infinity. So HAC is T naught minus T infinity. So this is our equation. So so we can, for long fin, we can say epsilon equals to what is the value of Q fin for long fin? It is under root HP KAC theta naught divided by HAC theta naught. What we have here is, now we are remained with theta naught gets cancelled. Kp upon HAC. So this is the value of effectiveness, if I am not mistaken. Okay. Oh, in the previous here there is a mistake. Here it is surface area. Okay. So surface area we can write it as perimeter into length. So when this will get converted into perimeter, what we will have the value, let me erase it. When we put this value of surface area into this equation, we have the equation of under root of KAC upon HP into 1 by L. So similarly here we had this value of ml because this L gets carried forward here. So that was my mistake, and I hope you now have cleared that point. Okay, so this is the value of effectiveness. Now what is the importance of effectiveness? So to understand the importance of effectiveness, just look at these expressions that I am writing here. If if epsilon or effectiveness is greater than 1, then we use fins. Then the fins are effective. And if the effectiveness is less than 1, then the fins are ineffective. And we do not use ineffective fins. So it is better to keep the system unfinned than providing ineffective fin. So always the fins are provided if its effectiveness is greater than 1. So I hope you got these points. Let us just quick have a quick recap and then we can move towards the problems. Okay, so first of all, we saw what was lumped heat analysis. Lumped heat analysis was carried out when when there is no temperature gradient, within the body, and which causes the conductive resistance to be negligible as compared to the convective resistance. And to achieve this, we need small bodies made up of highly conductive materials. After that, we derive this very important equation, ln of theta 1 by theta 2, HAS minus HAS upon rho VC into T. Then we modified into this second form. This is our first form. The second form was of time constant. Time constant, what is its significant? I told you that it tells you the amount of time taken by the body when it is exposed to ambient to reach the temperature of the ambient. What is the characteristic length? Then there was this form, the third form, which included characteristic length. Characteristic length is volume upon surface area. For characteristic length, especially, I told you to remember these two values. Of cylinder and of sphere. So these two values are really important. For cylinder, it is r by 2, and for sphere, it is r by 3. What is r? R is the radius of the respective body. Then we saw two important dimensionless numbers, Biot number and Fourier number. What is this Biot number? Biot number is the ratio of internal conductive resistance to the convective resistance. Conductive resistance to the convective resistance. It is given by HLC by K. The important condition for lumped heat analysis is Biot number should be less than 0.1. Then we saw Fourier number. Fourier number, what is Fourier number? Fourier number is the ratio of heat conducted to the heat stored. So FO is alpha T upon LC square. This was very important while deriving the fourth form. The fourth form is minus BI into FO equals to ln of theta 1 by theta 2. Now what is theta 1 by theta 2? I told you theta 2 and theta 1 are essentially the temperature differences. Theta 1 is T1 minus T infinity and theta 2 is T2 minus T infinity. Then we saw fins. Fins are nothing but extended surfaces which help in increasing your convective heat transfer. Then we find out these important formulas for long fin and short fin. Short fins are also sometimes referred as insulated tip fins. Please always note that the short fin has a complex formula as compared to the long fin. Then we saw temperature distribution, fin efficiency, fin effectiveness, and let's now directly move towards our questions. Okay, so the question here was asked in GATE 2014 in first session. The question says that the Biot number signifies the ratio of, what does the Biot number signifies? I told you that Biot number is the R conduction upon R convection. So this says that it is the ratio of convective resistance in the fluid to the conductive resistance of the solid. No, this is not the case. The conductive resistance in the solid to the convective resistance in the fluid. This is the correct answer. So this was asked for 1 marks. 1 mark. So this kind of questions may get asked on simple concepts that you guys must remember. So this is very important concept here again. Okay. So the second question we have here is of fins. So the heat loss from the fin, Q fin, is 6 watt. This was asked for, I think, 2 marks. 6 watt. This was asked in GATE 17 in second session. So the Q fin is 6 watt. The effectiveness and efficiency of the fin are, effectiveness is 3. So the fin is effective and the efficiency is 0.75. The efficiency is always less than 1 or less than 100. When we talk about in percentage, it is less than 100. When talking about in decimal or fraction, it is less than 1. The heat loss from the fin, keeping the entire fin surface at base temperature. So what what is it asking? It wants us to find out Q maximum. So what is the equation of Q maximum that we have? We know that epsilon is Q fin upon Q max. So this is 3. Q fin is 6. Q max, I told you that if this fin, now this is the fin with root temperature T naught, if this fin is kept at the entire temperature T naught, we can get Q max. So Q max is what? 6 by 3, which is 2 watt. So this was the question about fin. Now there is this third question we have of this is actually quite complex type of question that we are looking here. The question here says that there are two cylindrical shafts A and B. The both are initially at same temperature. They are placed in a furnace. The surface of the shaft remains at the furnace gas temperature at all times after they are introduced into the furnace. The temperature variance in the accelerator can be assumed to be negligible. The data related to the shafts A and B is given. Okay, see, this line is very crucial. What these lines tell us is that the temperature variation in the axial direction of the shaft, that is, the temperature gradient dt by dx is equals to 0. So what we can say that we can go for lumped heat analysis, right? So what we can say here is Let us just move it a little bit up so that we get space to solve our question. This is a large question. Okay, let it be. Now this table gives us the data about everything. Fine. We know that Fourier number is equals to alpha t upon LC square. And this question asks us to find out. Let us see what it further say. I haven't read it. The temperature at the center line of the shaft is 400 degrees Celsius after 2 hours. So after 2 hours, one of the shaft, that is shaft A, reaches the temperature of 400 degrees Celsius. And we have to find out the time required for the center line of the shaft B to attain the temperature of 400 degrees Celsius. Okay. So what time will the shaft B will take to reach the same temperature? So the related regarding time, we have this formula. Fine. So what is alpha? Alpha is K upon rho C. Finding alpha for A, put the value of K. What is the value of K? K for it is 40. Now it is volumetric capacity, joule per meter cube per Kelvin, which is nothing but rho C. Rho into C is volumetric heat capacity, which is given to be 2 into 10 raised to power 6, which comes out to be 20 into 10 raised to power minus, or I will just wait a minute. I can write it here. Alpha A is equals to 20 into 10 raised to power minus 6. And alpha B, similarly, putting K equals to, from this table, 20 divided by 2 into 10 raised to power 7. So alpha B comes out to be 20 into, sorry, 10 into 10 raised to power minus 7. Now this is the question of dimensionless number. There are two shafts and we are comparing them for the lumped state analysis. So we can equate the Fourier number of A with Fourier number of B. There is another thing, LC. Since both are cylinder, so LC is R by 2. For LC for A will be, now listen carefully, here it is diameter. So its radius will be 0.2 and LC will be 0.1. And for similarly, it is 0.05 and LC will be R by 2, which is 0.025. So in this equation, putting the values of alpha A, LCA square multiplied by TA equals to alpha B into TB upon LC B square. What we have is 20 into 10 raised to power minus 6 into 2 upon 0.1 square equals to 10 into 10 raised to power minus 7 into T of B upon, what is LC? 0.025 ka square. We can write it 2.5 into 10 raised to power minus 2. So this will become 4 and this 10 raised to power minus 2 will cancel out. Then we will have 10 raised to power minus 5 here. So this will just remain 10 raised to power minus 1. This will become 5. 5 into 10 raised to power minus 1 into 2. And here we will have 10 raised to 2 hours. 2.5 hours will be your answer. If you solve this question, you will find the answer to be 2.5 hours. So whenever solving the problem, I request you to utilize the calculator as less as possible, because the using calculator is pretty much hectic job. Always practice the manual calculation method, which we are not very much used to when we are in university, because our calculus are pretty much convenient to solve. But while solving in GATE, please try to minimize the use of calcium. So with this, I will end today's session. There were some disinterruptions of voice for which I regret and I apologize to all of you. And we will end our session here. Thank you for being here. Thank you very much.